Hello, I'm John Marini from the University of Minnesota in Minneapolis and St. Paul, and I'll be speaking on micromechanical causes of tissue injury. Since the year 2000, we've been aware that using large tidal volumes, especially when associated with pressure, can cause tissue damage. And recently, we've been concentrating on power and strain. Currently, cumulative injurious strain is what is believed to cause ventilator-induced lung injury. Now, we must remember, although we use them every day in practice, acting alone, none of the energy components fully accounts for ventilator-induced lung injury. If you look at the colored area on this illustration, you have resistance work and elastic work and a work component that's related to PEEP. If we consider tidal volume, plateau pressure, or driving pressure alone, none of those, especially if not considered with respect to the vulnerability of the tissue, will predict successfully the VILI risk. Pressure, which is very customarily used now, especially driving pressure, is only partly responsible for damage. If you take a static pressure, you must increase its volume with the additional pressure increment in order to rupture the balloon in this case, in this illustration. Notice at the moment of rupture, the balloon does not fracture uniformly, but along its stress lines, and we'll come back to that as we proceed. If we do not consider the compliance and the elastance of the individual lung unit, we may make some mistakes. If I try to inflate that non-compliant box with a very high plateau pressure, very high driving pressure, I do not succeed. I don't cause damage. I don't cause any volume change. This is also true within the lung. Let's consider moving from a PEEP of 5 to a PEEP of 25 in two conditions. The damage from a given driving pressure, which is the difference between those two, depends on the effective lung unit compliance and the resulting expansion, just as with a balloon. If we have a compliant lung unit and we apply 20 centimeters of driving pressure to a plateau pressure of 25, we have a large volume change, a high energy input, and I'll come back to that, and an overstretched situation. If we have a non-compliant lung unit for one reason or another, the same driving pressure and plateau pressure results in a small volume change, a low energy input, which is the product of pressure and volume, and tolerated strain. Another important thing to consider is that excessive driving pressure or energy, when you do consider the volume in each cycle, without considering the frequency with which it's applied or for the duration, is giving you only half of the picture. Another piece that I'm not going to touch much on right now is the rate of pressure conversion between pressure and flow is important. For example, if you took a cup of coffee and stepwise moved it downstairs, nothing would happen. You just move the cup of coffee. However, if you dropped the coffee cup from the uppermost landing to the lower landing, you might fracture it. The rate of pressure conversion is important. The same driving pressure, the difference between the plateau pressure and the PEEP, results in a very different outcome. Now, this may be especially important on the expiratory side of the ventilation cycle, which to this point only very few laboratories have been exploring, but may be quite important. It's the last I'll touch on that in this short presentation. Something that I want you to consider also is that the risk from high energy input or power, however you numerically measure them, may be totally conditional. Just as this gun cannot cause damage unless you load the cylinder, there will be no damage resulting from any numerical value of energy and power. Here's what I mean. If you take the elastic work and the resistive work, this is the energy put into the system, and look at the first part of the energy that's put in, it may be quite innocuous. Not much is happening at lower strain levels, lower pressure levels. But once you cross a threshold at the alveolar level, then some component of the energy per cycle and the power per minute becomes damaging. A stress threshold must be crossed before energy and power become overt. And the reason I say that is that if you look at experimental data, these are in rats and by Lex and Uhlig, showing that uh, injury it only occurs once you cross a threshold of 24 centimeters of water to 27 centimeters of water, then a dramatic change occurs. Same thing is true for not just pressure, but for power. For example, if I look at 52 hours at a very high tidal volume, but the strain is within a certain limit, 1.87 here, not much happens to the lungs at the end of 52 hours. But after only 20 hours at 45 milliliters per kilogram, which is a larger tidal volume, a higher strain, complete devastation of the lung. And what do you notice here then? It's that a threshold for strain must be crossed. That's also true within the lung. At the bottom of the lung, you have transpulmonary pressures and strains that are different from those in the upper parts. You might expect that these down here would fare better than those up there. In other words, the ventral alveolar units are subjected to greater transpulmonary forces, so why wouldn't they damage more? Well, in fact, in the laboratory, as we've shown almost 25 years ago, if you ventilate in the supine position with excessive tidal volumes and low levels of PEEP, the damage all occurs in the unexpected zone, in the dependent zone. The transpulmonary pressures are measurable, I suppose, from airway pressure minus pleural pressure. However, the actual strain is much greater dependently than it is non-dependently. These areas are preserved. The anterior regions are preserved. The dependent regions are devastated. And therefore, we must assume that the micromechanics make a difference. Now, in a recent paper, we talked about the components of energy and therefore of power that make a difference. I'd refer you to this paper to read more about that. Now, all but a minor fraction of the stored parenchymal energy is accounted for in expiration. In other words, we can measure the flow resistive piece in red and the PEEP related piece of energy in blue when we start from a plateau pressure. That's the product of pressure and volume is the stored parenchymal energy, but we can't account for the absorbed energy, which is unfolding of lung units, deformation of lung units, overcoming surface forces, viscoelastance, which may be innocuous, but also tissue damage, because you cannot create or destroy energy. Energy that you can recover does not cause damage. How could such a small amount of retained energy account for ventilator-induced lung injury? Well, there are multiple power amplification mechanisms, and I'll be talking about those in a minute. There's also a possibility that just mechanosignaling between the interstitium and the cellular interior may result in inflammation, but I'm not going to talk about that as I finish up. Let's talk about the reduced ventilating capacity of the baby lung as an amplification mechanism. If you take the same amount of power, 4 joules per minute, and you achieve a pressure of 30 in this lung, which is normal, not much happens. If you have severe ARDS and have a small baby lung, the same pressure, the same power, measurable power, has a specific power much, much greater than that 4 joules that you can measure because it's concentrated on the small piece. And I'll come back to that at the very end. The point is that the baby lung size is important when we're interpreting the power that we're measuring externally. At a constant tidal volume, the size and strain of the individual units of the baby lung change with advancing injury. Now, as injury worsens, the same volume going into 3 goes into 2, goes into 1, which with much different effects on total strain. And again, this is a part of the shrinking baby lung that I'll talk about in a moment. Some baby lung units may be protected, not made vulnerable as injury advances, because they're embedded within uh, damaged units that support the expansion of the lung unit and prevent it from reaching damaging proportions. So simultaneously with the increasing tendency for damage is an increasing tendency for protection. And that's where the baby lung may stabilize. Talking about geometrical power focusing by non-symmetry and viscoelastic drag, which is flow dependent, let's use this image. If you have an unyielding part of the lung surrounded by lung units that are tugging on it, then the geometric stress focusing is impressive. And if you do it faster rather than slower, you get also more problems. That's the viscoelastic drag. I don't want to spend too much more time on this, but this is a micromechanical force that's been talked about by Mead and by Walter Zinn and others who are describing what happens in the damaged parenchyma. Now, this is an important mechanism that very few people consider. This is the sequential loading by dropout of parallel stress-bearing elements of the extracellular matrix. If you look at the electron micrograph of a rabbit lung, you will see that the matrix is actually multifibrillar. It has multiple stress-bearing elements that are exposed to a given stress, and those units are weaker than others. Some are weaker than others, or may be subjected to higher effective local stresses than experienced elsewhere, just as we saw in the balloon. If you have a fixed amount of stress, let's call it 12 kilograms of weight, supported by 6 ropes, 3 of which are frayed, and those frayed ropes rupture, they put more stress on the parallel units that are still intact, and the strain and the stress both increase. So shared stress means that progressively increased strain and dropout happens with sequential failure of the weakest elements. Repeated cycles of damaging power and strain, just as in a bout of boxing, will cause the fibers to disappear as support elements and eventually break. If the cycle strain, which we've talked about before, is greater than the threshold, the frequency and duration of their application per cycle become important. And you can see that in the laboratory as we compare a lung experiencing high tidal airway stresses at a slow frequency and a faster frequency. You can see that for the first 10 minutes of the experiment, the same conditions cause equal changes. But as we advance in time, there's a tearaway exponential function of the progressively damaging lungs that are treated with more power and more frequency. Is matrix dropout another stress-raising mechanism? We believe so. So lastly, the power concentration by the shrinkage of the baby lung. As we go from the original baby lung size, aerated lung size over time, for reasons I mentioned before, the shrinking baby lung concentrates power and causes trouble, and that was just published this month. So I want to emphasize with my last slide that a suprathreshold pressure and strain elements is necessary, power is necessary, and duration is necessary. They're interlocked triumvirate of ventilator-induced lung injury. You don't get one without the other. And I will thank you for your attention.